Hi, I'm Trent Parado, Public Affairs Officer for NASA's Science Mission Directorate in Washington, D.C. I'd like to welcome you to today's news conference where we'll be discussing the latest discovery by the Chandra X-ray Observatory about an exceptional object in our cosmic neighborhood. Chandra is one of NASA's so-called great observatories. It allows scientists from around the world to obtain X-ray images of exotic environments to better understand the structure and evolution of our universe. For those joining us online, you can find out more information on www.nasa.gov/Chandra. As for the order of events today, we'll have 5 panelists joining us. Each will give a short briefing, and then we'll open the phone lines for questions and answers. I'd like to take a brief moment just to welcome and introduce the panelists. First, we have John Morse, Director of the Astrophysics Division, NASA Headquarters in Washington. Next, Dan Patnod, astrophysicist at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. Next, Avi Loeb, astrophysicist at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. Kim Weaver, astrophysicist at the Goddard Space Flight Center in Greenbelt, Maryland. And joining us by phone is Alex Filipenko, astrophysicist at the University of California, Berkeley. And with that, I'll hand off the discussion to John Morse.
Thanks, Trent. Now, some missions are like good wine. They improve with time. And the Chandra X-ray Observatory is certainly one of our gems. If we could have the first graphic, please. Now, more than 11 years ago, Chandra was put into orbit by the STS-93 shuttle crew. And here we show the launch video back in 1999. And then this is the deploy on orbit. And that booster stage right there put Chandra into its final science orbit, which takes it all the way up to 44,000 miles above the Earth and then swoops back in every orbit. And it spends most of its time doing its science away from the Earth. Now, even starting with the first light image, there has been extraordinary wealth of data coming from this truly great observatory. So let's briefly look at some of the iconic data coming from Chandra over the past decade. In the first graphic, we have the Cassiopeia supernova remnant. And this is an exploded star in the neighborhood of the sun, not too far away. And it shows us very graphically how the elements are born inside the stars and then distributed out into the interstellar medium. And the colors in this image actually tell us what the elements are, whether it's oxygen or iron and so on. In the next image, this is the Crab Nebula. And this shows swirling electrons around the pulsar at the middle of that exploded star. In the next image, we have the center of our galaxy. And Chandra has probed the workings of supermassive black holes at the centers of galaxies, including here in Sagittarius, in our own center of the Milky Way. In the next image, we have the Bullet Cluster. Here, shown in the red, Chandra has mapped the X-rays coming from the hot normal matter as galaxy clusters collide out in the cosmos. And it has shown how it differs from the blue, which is mapping of the dark matter in this region. And it shows us how the normal matter and the dark matter actually behave differently. It doesn't tell us what dark matter is, but it's a very important clue as to its nature. And in the final image, this is a deep field showing us the X-ray glow from objects such as distant quasars. It tells us about the distribution of black holes throughout the universe. And Chandra is even responsible for making the only other independent measurement of the dark energy in the universe. So it's not surprising that Chandra scores well, and in our most recent senior review of operating missions in astrophysics, it was right at the very top for its science impact. And so now let's hear about another one of the science results from Chandra. Let me turn it over to Dan.
Thank you. So today what we'd like to do is report on evidence for the detection of what might be the youngest black hole observed in our own cosmic neighborhood, born in a core collapse supernova. This supernova was observed about 30 years ago. Now, core collapse supernovae are associated with the deaths of massive stars, and it's believed that at least some of these events can result in the formation of black holes. Results such as this might actually be important because we don't know what the dividing line is between those supernovae which form black holes and those which form neutron stars. This is something my colleague Avi will discuss in a few minutes. Now, this particular supernova, supernova 1979C, was observed in April 1979 by an amateur astronomer named Gus Johnson, who's a school teacher from nearby Swanton, Maryland. He was observing the nearby galaxy M100, which is shown here in the Digital Sky Survey, and then again in the VLT. And now, as you see in X-rays, where supernova 1979C is actually seen, he was observing it just because this is what he liked to do. And at the time, his was only the third discovery by direct detection of a supernova. So in X-rays, it's been observed with several observatories. First with Einstein X-ray telescope in 1980, which actually didn't detect it, and then later on in 1995 with the Rosat X-ray telescope. Now, between observations with Rosat and now, there have been several observations done with Chandra, XMM Newton, and also Swift. And while it isn't unusual to observe X-rays coming from a young evolving supernova, what is interesting is that the X-ray emission from this particular object has remained remarkably steady. In addition, while it's also been steady, it's also been extremely bright. And we interpret this high luminosity or high brightness as evidence for accretion of supernova material back onto the black hole. Now, when we speak of accretion, what we're talking about is material that's being fed back onto something. And in the case here, as it's accreted onto the black hole, it heats up to very high temperatures and becomes very bright in X-rays. In the case here, we can use the brightness of the accretion onto the black hole to find out that this black hole probably has a mass of around 5 times the mass of our sun. So the question becomes, why is it that we think that some of the X-ray emission that we're observing, or most of the X-ray emission that we're observing, is coming from accretion onto a black hole and not by some physical mechanism? Well, as it turns out, there are actually several mechanisms for X-ray emission from a supernova. One is that you have the blast wave just expanding out into the progenitor's wind. And in this case, the blast wave will heat the surrounding material to high temperatures. The problem with that interpretation that we found in this case is that as the blast wave expands, the X-ray emission should actually decrease with time because it's expanding, the blast wave is expanding into less and less material. If we had observed that the X-ray emission was fading, we might actually be comfortable with that interpretation, but as it is, we weren't. So another possibility is that when this star exploded, it formed what's called a magnetar. Now, a magnetar is just a special type of neutron star with an extremely high magnetic field. And the idea is that as this magnetar is formed, it loses some of its rotational power to the, it loses some of its rotational energy and powers the light curve in X-rays. The problem here is that, once again, the X-ray emission is actually going to be assumed to decrease with time. And we developed a model for what the magnetar emission should look like over time, and we found that we're about a factor of 10 times brighter than what the model predicts. So, excuse me. Now, while our observations are consistent with that of an accreting black hole, there's actually another intriguing possibility, and that is that we're looking at something called a pulsar wind nebula, such as the Crab Nebula in our own galaxy. In this case, instead of looking at something that's actually accreting material, we have a rapidly spinning neutron star that's sending out very high-energy electrons and other particles out into the surrounding material. And in that case, we're actually looking at the emission from that star we're actually looking from the wind rather than from the accretion. In any case, whether it's a pulsar wind nebula or a black hole, we're looking at one of these objects in its infancy, and that in and of itself is exciting. So we have ideas as to how we can actually test these various theories. And we have observations which are coming up in the near future. And if we find that this particular object is still as bright as it's been for the last almost 20 years at this point in X-rays, when you account for the fact that it was only redetected in 1995, we plan on maybe getting a longer observation where we can actually look at a detailed spectrum of this object and test whether the X-ray emission is coming from some sort of central compact object or the blast wave, or possibly, or likely a combination of both. So with that, I'd like to turn over the speaker to Avi. Thank you.
So we are here to discuss a question that is often asked in Hollywood. How do stars end their life? Except we're dealing with real stars. And when a star is 10 times more massive than the sun, or even more than that, the core of the star may collapse at the end of its life. Once the nuclear fuel is consumed near the center of the star, the core collapses, loses pressure support, and collapses upon itself due to its own gravity. And it can end up in one of two ways. Either it makes a neutron star, which is the densest form of matter that we know about. It has the density similar to that of an atomic nucleus and a size comparable to that of a big city. Or it ends up in a black hole, which is an object to which you can get in but can never get out of, sort of the ultimate prison. And theoretical astrophysicists were debating for many years about the boundary between a star that can make a black hole and a star that can end up as a neutron star. And the fate of the star depends on many factors, most importantly, the mass of the stars. It can also depend on whether the star has a companion, whether it rotates, and so forth. The progenitor of supernova 1979C is estimated to have been a star with 20 solar masses on the boundary that theorists postulated for the transition between a neutron star and a black hole. And so it could very well have been the progenitor appropriate for making a black hole. This particular supernova belongs to a rare type of these explosive events that includes about 6% of all core collapse supernova. These are called type 2 linear supernova, in which the light curve peaks and then declines steadily by many orders of magnitude. In difference from the more typical types of supernovae that reach a peak, decline a little bit, and then remain steady for a long while. These are called type 2 plateau. Now, about 20% of all core collapse supernova are believed to end up as black holes. And it is believed that stars more massive than about 20 or 25 solar masses end their life that way. If our interpretation is correct, and indeed supernova 1979C ended up as a black hole, then of course it's the first time that we're seeing a black hole being born in a normal supernova. It has been conjectured for a while that black holes do form in explosive events that take place across the universe. These are called gamma ray bursts. In these events, the core of the star may collapse to make a black hole, and the black hole produces jets of matter moving at a speed close to the speed of light. And those jets penetrate through the envelope of the star and eventually get out, so that if an observer is lined up with the jet, it would see a gamma ray flash. And we call these gamma ray bursts. We see such flashes roughly once a day coming from the edge of the universe. However, in this particular event, there is no evidence for a gamma ray burst. So it's the first time we see a black hole being born in a normal supernova. Now, the luminosity that we observe in X-rays is close to the limiting luminosity that a black hole can have. So if you feed a black hole with a lot of mass, in this case, the black hole may be fed by a disk of material surrounding it, either as a result of material that was left behind from the supernova explosion, or as a result of a binary star companion that donates mass to this black hole. In that case, if the luminosity coming from the vicinity of the black hole exceeds a certain limit, the force acting on the material outward would push the material and not allow it to accrete onto the black hole. And so there is this very natural characteristic luminosity that you would expect from a black hole that is fed well. And this is roughly the luminosity that we see for the typical black hole masses of 5 to 10 solar masses that one expects from such events. Now, it will take the black hole about 40 million years to double its mass. And so we cannot really trace a change in the mass of the black hole during the course of the observations, the 31 years that we have observed this source. But the fact that the luminosity is steady is a clear indication that we might be seeing a black hole accreting at its limiting accretion rate. And in particular, what we have are photos of this source during the first 30 years, during its infancy. These photos are labeled by the age of the source, even though it took them a long time to reach us, as we observe them today. If this is indeed a black hole, then there are several important implications. First, to the basic question of how supernovae explode. There are two possible energy sources for an explosion. It could either be a central engine, just like the black hole, that somehow releases energy into its vicinity and powers it. That's how a gamma ray burst takes place. Or it could be radioactive material that is produced in the supernova that is powering the light curve of the supernova. And so understanding the way that supernovae explode and which fraction of them end up as black holes and which fraction end up as neutron stars is very important for our theoretical understanding of these important events. Theorists for many years had a difficult time exploding massive stars on the computer. And it's quite possible that they were right, that in fact a fraction of those explosive events end up eventually imploding and making a black hole. We don't know the relative statistics of black holes and neutron stars to a very good precision at the moment. And so observing events like that are very important in terms of calibrating the statistics. In addition, black hole and neutron star binaries are important sources of gravitational waves. And there are observatories being constructed to detect these waves. And so we would like, of course, to know the abundance of black holes and neutron stars. And overall, we're dealing with the properties of matter at extreme conditions, at very high densities, close to that of an atomic nucleus. And we cannot really reproduce these conditions in the laboratory. And so by observing the sky, we're able to learn about environments that cannot be reproduced in the lab and that can only be observed out there in the universe. Of course, if we go back in time to the very first stars, for example, the conditions there were different. It's quite possible, as some theorists argue, that massive stars were much more abundant at early times, and so the formation of black holes may have been much more frequent at early cosmic times. And I will turn the stage to Kim.
Thanks, Avi. Thanks, Dan, for explaining this exciting result. What is it that really matters in terms of this result? It's not just that possibly we have found the youngest nearby black hole. It is a young black hole, but what's really exciting about it is that we know the exact birth date of the black hole. We have found for the first time possibly the true birth date of a black hole. And you may ask, well, aren't black holes in the early universe younger perhaps than this one? Certainly there are black holes that are forming all the time. And in the early universe, there might be very young black holes, but do we know their exact age? Do we know exactly how old they are? No, it's very difficult to do that. When light has traveled billions and billions of years to reach us, it's hard to say exactly when a black hole that we're looking at was born. So this is a very important result to be able to pinpoint the birth date of a black hole for the first time. And for me, in terms of studying black holes, what's exciting about it is that we know it's very young. It is in its infancy if it is a black hole, and we want to watch how this system evolves and changes in its youthful stages from when it's first born to when it goes into a child and a teenager and gets older and accretes more material, because that's how we understand the physics of black hole systems. So that's very important. The other thing that's kind of neat about this story is it is a story. It's a story of science in action. And you've heard a little bit about the description of the observations, when it was observed. It was observed many times since with NASA satellites and other observatories. And so astronomers around the globe have taken images and data from this object and over time have put together this story. which is sort of like a detective story, taking pieces of the puzzle and putting them together and finally determining that, yes, indeed, we've almost solved the puzzle now. We just need a few more pieces, so we're very close to understanding the true source, the genesis of this compact object in the center of this supernova explosion. So that's very exciting. It's in its infancy. We want to understand accretion and energy production in this object. The thing that's interesting about supernova 1979C is that it's very difficult to see these objects, even if there were many of them out there in our galaxy, for example. When a supernova goes off, it fills its region with material, and so it might be difficult to look inside and see through the obscuration to see the black hole being formed. Also, the light, the integrated light from that supernova event might be too bright and might get in the way of seeing the light from the black hole accretion anyway. So it probably takes about 4 to 5 years before you can really see the X-ray light coming out of the material around the black hole. That makes this object actually perfect for detecting because it's roughly the right age to be able to see that X-ray signature pop out. So it's a wonderful opportunity for astronomers to look at these young systems, and I hope we can find many, many more of them. And now that we know a way to do that by using X-ray data, hopefully astronomers will begin to look through the data and see if we can find more. So what is the implication for finding more baby black holes in the universe? Again, this is the first direct evidence for one, the first strong direct evidence. So to me, it's sort of a new population of youthful objects. You know, I'd like to be able to see more young black holes because I want to understand what's happening right after they're born. And they probably are very common. Another important tool here is the X-ray spectrum itself. We see what we believe to be the X-ray spectrum of accretion around a black hole. There are many objects out there that are compact that we think might be black holes, but we're not sure. And the only data we have are X-ray spectra. So if we really know that this is one, then we can take this spectrum and match it to the other X-ray spectra and see if they look the same. And if they do, that's a very good indirect way to say, oh, these other things are also black holes. So I think that this discovery is going to help astronomers add to our census of the number of black holes that we know about in the universe. And I'll turn it over to Alex.
Tim said, this is an exciting discovery. A very young black hole, born just 31 years ago as seen by us. So here we have essentially a baby picture of a stellar mass black hole, one that is about 5 times the mass of the Sun. Those are the stellar mass ones, as opposed to the supermassive black holes in the centers of galaxies. Now, we know of several dozen stellar mass black holes in our Milky Way galaxy, and there are probably millions of them in each big galaxy, but we don't know their ages. Most of them are probably millions or even billions of years old. So here is one whose age we actually know, and by continuing to observe this object, we will be able to study how young black holes behave, and especially how they swallow gas from their immediate surroundings, how they accrete this gas. Now, as Avi said, it's important to distinguish supernova 1979C from another way of producing stellar mass black holes, the so-called gamma-ray bursts, or GRBs. Now, gamma-ray bursts are sometimes called the birth cries of black holes, and it's true, we do indeed think that many of them produce stellar mass black holes. But we still don't have any direct evidence that they produce black holes. We have not yet detected the putative black holes in these objects. Gamma-ray bursts produce black holes through the merging of 2 neutron stars, or through the collapse of a single extremely massive rotating star. But such events are extremely rare. Supernova 1979C, on the other hand, may be a more typical way in which massive stars produce black holes. Now, another interesting difference is that GRBs generally occur billions of light years away and billions of years ago, whereas supernova 1979C occurred in the relatively nearby beautiful galaxy M100 in the Virgo cluster, only about 50 million light years away. So in a sense, this object is almost in our backyard compared with typical GRBs. We'll be able to study it in much more detail. We'll be able to study this accretion process. As Avi mentioned, supernova 1979c was a relatively rare type of supernova, a so-called type 2 linear. These kinds of exploding stars are only about 5 or 6% of core collapse supernovae, and moreover, only a small fraction of them probably produce black holes at their center. The others produce a very dense type of star known as a neutron star. But astronomers don't yet know what the dividing line in mass is between the types of stars that produce neutron stars versus those that produce black holes. We just don't know what that dividing line is, but it's important because we want to understand how exactly black holes are produced. The star that formed supernova 79c probably had an initial mass of about 20 solar masses, and this might be very close to this dividing line in mass. Now, there are certainly other variables, such as how mass is lost from the star prior to the explosion, and whether the star is in a binary stellar system. Supernova 1979c, in fact, may have been in a binary stellar system. But in any case, the supernova will help astronomers determine which stellar explosions make black holes and which ones make neutron stars. And this will also tell us about the nature of matter at very high densities, and we can't study that in terrestrial laboratories. You can't go to the hardware store and buy a neutron star. Whereas here we have a case that may be telling us the dividing line at which point a ball of matter becomes unstable and gravitationally collapses to form a black hole. The final possibility I want to mention is that, as Dan said, this might be powered by a pulsar wind nebula, not necessarily by accretion onto a black hole. But to me, that would also be interesting, because this would be the youngest known pulsar wind nebula. Now, a great example of such an object is the Crab Nebula, which is nearly 1,000 years old. It's the remnant of the supernova that was studied by Chinese astronomers in the year 1054. And it's been studied by astronomers in great detail. What we see in supernova 1979c may be a very young version of the Crab Nebula, and it will help us understand the evolution of such objects through time. So I'm pretty excited about this discovery, regardless of whether it turns out to be a young black hole or a pulsar wind nebula. We should keep on observing it to learn more about it. Thanks.
Okay, great. Thank you very much, Alex. Now we're going to move on to the question and answer session. For all participants, please identify yourself and your media affiliation before asking your question. And if possible, direct your question to a specific panelist. For those joining by phone, you can signal the operator that you have a question by pushing the *1 keys on your telephone. And we have a number of press online with us, so I'd ask you to please limit yourself to one question to start. I understand that we have a question on the phone from Seth Bornstein from the Associated Press. Seth, go ahead.
Thank you so much for doing this. I guess this would be for Avi or Kimberly Weaver. It's a two-part question then. First is, if this is indeed a if it is not a black hole and is a pulsar wind nebula, are pulsar wind nebulas more rare than black holes in our cosmic neighborhood? In other words, which is more rare? And then the second part is, if this is a black hole, would this be the smallest mass of a star that led to a black hole that we've observed so far with the 20 mass of the star that involved here? Thank you.
So this is Avi. Pulsar wind nebula are much more common, are expected to be more common than black hole remnants, simply because only a small fraction of all core collapse supernovae end up in a black hole. That's, of course, a theoretical estimate, but it also backed by data we have on the frequency by which we observe evidence for black holes in binary star systems. Now, to answer the second question you had, can you remind me?
Yeah, the small. I could just jump in. This is Kim. In terms of this being possibly the smallest mass star that has ever made a stellar-sized black hole, we don't know the answer to that because it's not clear what the masses of the progenitors really are. And this is a piece of data that's going to help us understand that sort of limiting mass between making a black hole and a neutron star. So we don't know the answer, and these data will lead us to the answer to that question.
Okay, great. Thanks very much. Let me just check and see if there are any questions here in the audience. No? Back to the phones. Just a reminder, hit *1 on your telephone if you have any questions for us. Okay, Kristen Minogue from Science Magazine, you're on. Go ahead.
Thank you for talking to us today. This could be a very obvious question, so if it is, I apologize for it. I'm curious, since the supernova occurred in a galaxy 50 million light years away from Earth, how do we know the age of the black hole is only 30 years old? How is that possible?
I'll handle this. So this is Dan. So when we talk about how old the black hole is, or how old the supernova is, we're actually referring to how old it is with regards to when we first observed it. So when we say it's 30 years ago, it means that that's when we saw it. Now, the galaxy is 50 million light years away, so in its own frame of reference, it occurred 50 million years ago. So
another way to put it is, if you are assembling a photo album of your family, you can have pictures in it that are labeled by the age of the person, rather than by the time it took these pictures to be put together in the album. So in our case, it took the picture to arrive to us a lot of time, but what we see is a picture of the object, of the source, when it was very young. And that's what we refer to as the age of the object.
Okay, great, thank you. The next question comes from Mark Kaufman, Washington Post. Go ahead, Mark.
Yes, so thank you very much. Just trying to understand something about the presence of the gamma ray burst type supernova and black holes that would be coming from them. Do those also exist and they occur in the Milky Way, or is this something that is, was further back in time and as a result would be very different in that sense?
This is Avi. Gamma ray bursts occur in all galaxies. They just occur much less frequently than supernova. Only a small fraction of all collapses of massive stars end up in a gamma ray burst. So in a galaxy like our own, we have to wait a long time before we will see one gamma ray burst. We only have to wait a century or so before we see a new supernova. And so it's only a question of how long you need to wait. Now, there are many more galaxies filling up the universe so that you don't have to wait that long if you were to observe the entire universe. So we are seeing a gamma ray burst every day simply because we are looking at many, many galaxies at once. The conditions necessary to make a gamma ray burst are very special. Not only that you need to make a black hole, the black hole needs to produce jets of material moving close to the speed of light. And the jets should be able to penetrate through the envelope of the star and reach the outside world before they slow down. So it's quite possible that some gamma ray bursts do not make it. Some fail and end up in a supernova explosion. We don't know in this particular case of a supernova whether that was the case, or perhaps a neutron star formed and then material fell onto the neutron star to make a black hole. It's, of course, possible that the black hole formed just at once at the beginning and then helped to power this very energetic supernova. This is one of the brightest supernova that we have seen.
Great, thank you. Our next question comes from Irene Klotz at the Discovery Channel. Go ahead, Irene.
Thank you very much. I was just wondering of which of these two theories you all think is most likely. You laid out a really nice presentation for what it would mean if it was a really young black hole, but it seems that that whole kind of line of reasoning might not even be right. So if you maybe can just put some context or some way of understanding which of these two theories you think is more likely. Thanks.
Well, I don't think that we can definitively answer that just yet. We have several years worth of X-ray observations, but the problem is that we don't have a very deep observation to actually look at what the emission from this source looks like in detail. And that's what we need to do in order to test one theory against the other. Right now, we can only look at the X-ray light curve over a long period of time and look at least qualitatively at its X-ray spectrum over that same period of time. And the shape of that spectrum is consistent with both an accreting black hole and also it's consistent with emission from a pulsar wind nebula. If you look at it for a lot longer, you would actually be able to distinguish between the two. So we can't rule out one or the other at this point.
And if I can add, the X-ray luminosity has a special meaning in the case of a black hole. It's the limiting luminosity that a black hole could have if it has a mass of order 5 to 10 solar masses. In the case of a pulsar wind nebula, you could have a variety of X-ray luminosities since the emission there is not powered by accretion. And so if indeed it's a black hole, the understanding of why we're seeing this particular luminosity is more straightforward.
Oh, and I'll add too, this is Kim. There are other supernova remnants that are being looked at to see if they can see evidence for accretion showing up. And so far, that's not been the case. So we're seeing something here that we've not seen in other objects, which leads me to favor, just personally, the black hole interpretation.
Let me just take a quick moment to remind folks that if you're participating online, you can find out more information about Chandra and this discovery at www.nasa.gov/Chandra and at chandra.harvard.edu. Let me take any questions in the audience if there's anything further. Okay, any questions by phone? Okay, then with that, we'll end today's media conference. I'd like to thank the panelists for their time today. Again, thanks to everyone for joining us, and have a great day.